All right, so today we're going to look a little bit more at vectors, some operations on vectors, and in particular, the dot product of two vectors. So first we're going to start by saying how can we represent vectors really quickly. You have your magnitude and your angle, where your magnitude is your length. So you can say it's something like 25 units at 40 degrees, and a lot of times we'll say from standard position, or you could say at 30 degrees west of north. Now this works really well when we're in 2 dimensions. The angle thing becomes a little bit trickier when we are in 3 dimensions. And then the other way, of course, is with your 2i plus 3j plus 5k. And your physics people are more likely to use your hat notation. And you can even, in calc, we can simplify it, which is probably one of the nicest ways, is right there with your 3 dimensions and your vector notation, like so. All right, so we're going to look at some of the operations on vectors. Probably one of the easiest in component form is adding vectors, but in geometric representations, maybe not quite so easy. If you think about adding, we take our A vector, say, and we wanted to add it to vector B, we have to put the tail of B at the head of A, and then my vector is that one motion overall, and the vector is that one motion itself. It's not the 2 separate vectors placed together, but it should be one line, and that's your A plus B. Now in components, that's much easier. You add your like components. It's fairly simple. Multiplying vectors, again, sort of physically representing, if I want 3a, a scalar times a vector, well, my magnitude is 3 times as big, because really you're laying it up here, and so your magnitude you multiply by 3, and your angle is going to stay the same. If I multiply by -3, of course, my angle changes directions. And then with your components, you just multiply each component. And that's fairly easy. And then as far as other multiplying, so this is multiplying by a scalar. And right here, when you multiply a vector by a scalar, you get a vector. So vector by a scalar, you get a vector. Now right here, our dot product, when we dot 2 vectors, we are going to get a scalar. And then there's another kind of multiplying. So multiplying 2 vectors together, if you dot them, you get a number, which is a scalar. And if you cross them, you're going to get another vector. And we'll do cross product in another lesson. So right now we're going to focus in a little bit on dot product, also known as scalar product, because it is the way of multiplying 2 vectors that gets us a number. So if we have 2 vectors, u, which we can represent as u1 in the I direction and u2 in the j direction, or again, we could say u1 comma u2, and then we have another vector v1 comma v2. So there's 2 ways we can get our dot product. One is our geometric definition, and as long as theta is between 0 and pi, because we're going to consider theta as being the angle between our vectors when they are tail to tail. So we have to be sort of in this position. Here's A, and here's B. And then theta would be here. And we will always choose the angle that's from 0 to 180 or 0 to pi, because we would never say that the angle between them is this. We always want to choose the smaller of the angles, and the smaller will be the one that's between 0 and 180. So that's sort of our geometric definition, where these, hopefully we know, represent the magnitude of u and the magnitude of v. So if you have a drawing, and if I know that, say this is 12, and this is 3, and the angle in between them is 20, it's very simple. Your u dot v would be basically 36 cosine of 20 degrees. And again, most of what we're doing now is in degrees. The one time in calculus we'll be using degrees primarily. You could also do it in radians. Okay. And that is very handy if you know your magnitudes and you know your angle in between. It's very easy to do. But this formula, very rarely do we actually know the magnitude and the angles. We are more likely to use this formula to help us find our angle between two vectors. The more useful, and especially because we really like using components, the algebraic definition to find the dot product, you basically multiply your I component times your I component for each vector, and your j component times your j component. Or if you're in 3 dimensions, the I coefficient times the I coefficient, the j coefficient times the j coefficient, and the k coefficient times the k coefficient, and we get a number. All right. So let's look at one very quick example. Here we are just in 2 dimensions, and we're going to show that the geometric and the algebraic definitions give the same answer. And that geometric is really more helpful in 2 dimensions. So if we look at the algebraic, we take, and again, if v, you could represent v by 1, 0, and this by 2, 2. So what we're saying is you multiply your I component right here times your I component right here, and we're doing 1 times 2. And then you add that to your j times your j, 0 times 2. And overall, we get an answer of 2. Now, algebraically, I can represent my v vector. It's 1 unit long and in the positive x direction. And then my w is going like 2 and 2 right there. And hopefully you recognize that if this is 2 and this is 2, then this angle must be 45 degrees, and our hypotenuse is 2 root 2. You could also use Pythagorean theorem and get root 8. But anyway, so there is my picture. And so to find my dot product, I'm going to take the magnitude of v, which was 1, and multiply by the magnitude of w, which was 2 root 2, and then multiply by cosine of the angle in between them, which is 45 degrees. And I do 2 root 2 times root 2 over 2, and voila, I get the same answer of 2. In class, we will do two separate proofs of why the dot product works, but for now we're just going to focus on the mechanics. So a few properties of the dot product. So if I have vectors u, v, and w, and any scalar number k, v dot w is the same as w dot v. In other words, dotting as an operation is commutative. And then number 2, v dot kw is the same as k times v dot w, which is the same as kv dot w. So we sort of have this associative property with respect with a scalar and 2 vectors. And then finally, v plus w dot u is the same as u dot v plus u dot w, and that's an example of what we call the distributive property. And in algebra, it's usually multiplication over addition. Here we have dotting, which is a form of multiplication over addition. All right, so let's look at a couple examples. And I think for our purposes, it may be easier to represent these in this notation. I have 0 i's, 2 j's, 1 k, and I have 1 i, 6 j's, 0 k's. Actually, I didn't need a at all for this one. And y is 4i, negative 7j, 0k. So when I'm going to do the dot product, I'm going to use the algebraic formula right here. And I take my I times my I. 1 times 4 is 4. 6 times negative 7 is negative 42. And I get an answer of negative 38. So that is my dot product. Now if I want, I can use that to find the angle between my vectors. We'll talk about that in a minute. Here we're going to do a dot c plus y. So let's do c plus y first. C plus y, I have 1 plus 4i, so that's 5i. And then I have 6 minus 7j, so that's negative 1j. And then I'm going to have a 0k. I need my k because a vector has a k component. So I'm going to dot my 0, 2, 1 with my 5, negative 1, 0. And as I do that, I take 0 times 5, which is 0, and 2 times negative 1, which is negative 2, and 1 times 0, and I get an answer of negative 2. Over here, we're going to dot C and A. And so I'm going to have 1 from the C and 0 times the A, so that's 0. And let's see, J and J is going to give me a 12. 6 times 2 is 12. And then K for my C vector is 0, so I get a 0. So this is 12. And A dot Y, I get 0 times 4 is 0. I get negative 14 from my J's multiplied together. And that's it. Minus 14, and I also get negative 2. And then the question at the bottom, what do you notice about 5 and 6? I got the same answer, and why? That's a little example of distributive property of dotting over addition. So they should be the same. All right. So here we have a dot b times a, and I'm not maybe going to do these, but let's see what kind of answers should we get. When you do a dot b, you are going to get a scalar, and when you multiply it times a vector, you are going to get a vector answer. And maybe we will quickly do this. It shouldn't take very long. Or we'll just say we get a vector. I'll leave this for you because this is part of your homework. What kind of answers would you get for 8 and 9? If you want, pause the video, see if you can come up with the answer. So here we go. 8. This is a dot y is a scalar. C dot z is a scalar. And overall, my answer will be a scalar. And number 9, dotting gives me a scalar. Multiplying it by a vector gives me a vector. But then I'm taking a vector dot a vector, and overall I will get a scalar. Okay, so the last thing we're going to look at, one of the main uses for the dot product is actually helping us find the angle between two vectors. If you have vectors in 2 dimensions, you can use a lot of triangle trig, law of sines, law of cosines, things to find the angles between them. It's not so easy when we are in 3 dimensions, but we can use the dot product, especially, oops, too many L's, in 3D. And what we'll say is, if we can calculate the dot product using our components, if we have our components, we can also calculate our magnitudes, and then all that's left is to solve for theta. And then the other thing we can do is determine if 2 vectors are perpendicular. And so to be perpendicular, what we would know is that they'd have an angle of 90 degrees, or pi over 2 radians, depending on how you think of it, which would mean the magnitude of u, magnitude of v, cosine of 90 degrees. But the cosine of 90 degrees, hopefully you know, is 0. So when u dot v is 0, your vectors are perpendicular. And that is the only way that your vectors can be perpendicular, is if their dot product is 0. And that also gives us a hint. If your angle between your 2 vectors is between 0 and 90, you get a positive dot product, because your cosine will be positive and your magnitudes are always positive. And if your angle is from, so this is positive cosines, and if I am between 90 and 180, I get negative cosines. So when you get a negative dot product, that is telling you that your angle between your vectors when they're tail to tail is greater than 90. So positive dot product means our angle is acute, and a negative dot product means our angle is obtuse. So let's look at one example of finding the angle between the vectors. So first I'm going to find my actual dot product. And so 1 times 5 is 5, 0 times 2 is 0, 3 times -2 is -6, and I get a dot product of -1. The next thing I need are my magnitudes, and to do that we do our version of the Pythagorean theorem, 1 squared plus 2 squared plus 3 squared, square root that, and that is the square root of 14. So that's the magnitude of A. I'm going to take the magnitude of B, which is 5 squared plus 2 squared, jumping ahead, and that's the square root of 29. And then it's cosine of theta. So -1 over square root of 14 times 29 is cosine of theta. And to find theta, I'm going to do a little inverse cosine action. I am in degrees, and I'm going to inverse cosine 1 divided by square root of 14 times 29. And my angle is 87.155. And that is very easily done. And knowing that I had that, oh, I forgot my negative. So I was going to say I had a negative answer. Let's try this again. I knew that if I had a negative dot product, I should have a negative, or not a negative, I should, that, I don't want this. Talking and typing sometimes is tricky. There we go, 92.847. That's better, because a negative dot product means an obtuse angle. Is that the right one? I think it was. 845. Let's try that. Rounding to 3 in AP Calc. So that should be it. I think you have enough to work on the dot product.